This is Module 4 of the Geometric Review and Design, or GRAD, training tutorials. This module is entitled Vertical Alignment and is pulled from Section 200 of the L&D Volume 1. In this module, you will learn about what is needed to design vertical alignments. There are basic design elements of vertical alignments that you will see in this module. This module will also allow you to understand how to design vertical alignments that meets a specific design speed. Finally, you will see example vertical alignment problems to show how the material in this module can be applied. As discussed in L&D Volume 1, Section 200, there are several elements of vertical alignments. Tangent grades are the straight lengths of an alignment. Vertical curves are used to connect tangents. This module will go into these elements in greater detail. Section 203.2 of the L&D Volume 1 discusses maximum grades based on functional classification, terrain, and design speed. Figure 203-1 shows these maximum grades in percent. Notice notes A and B below the table. Note A applies to interstates, other freeways, and expressways and gives the opportunity to increase the grades in this table by 1% in urban areas in extreme cases where development precludes the use of flatter grades. Reason is because it is often difficult to change grades significantly when development is close to the roadway, like usually the case in urban settings. Grades 1% steeper may also be used for one-way downgrades except in hilly terrain. The designer should check to ensure the horizontal alignment doesn't require significant change in direction, either within or immediately after the steep downgrade. Note B applies to collector streets and gives the opportunity to use 1% steeper grades when applying over short grade lengths, like typically 500 feet or less, and for one-way downgrades. For low-volume rural roadways, can increase the grades in this table by 2%. Using values that exceed these maximum grades requires a design exception, and the crash history should be reviewed if perpetuating an existing condition to determine if the vertical grade is contributing to the crash trends. Steep uphill vertical grades can have an impact on the traffic operations and can introduce a safety issue. Specifically, critical lengths of grade are those grades which a loaded truck can operate without an unreasonable reduction in speed, which is typically 10 miles per hour. Lengths that exceed these can create safety issues by introducing too great of speed differentials between cars and trucks on the same facility. When these lengths are exceeded, designers should analyze the impacts on level of service and complete the safety analysis. In those situations where trucks drop below the reasonable reduction in speed, truck climbing lanes should be investigated. Those truck climbing lanes should be extended beyond the vertical curve at the end of the critical uphill grade to maximize their benefit by allowing trucks to regain the reasonable speed threshold to allow it to merge into the through lane again. With the length of added lanes needed to preserve the recommended LOS on sections with long grades exceeds 10% of the total distance between major termini, consider constructing a divided multi-lane facility. Let's look at a real-world example of this concept. This is a proposed profile of a single-lane ramp for a system interchange project in Akron, Ohio. A design exception was taken for this ramp for exceeding the maximum vertical grade. Notice the plus 4.22% grade transitioning into a plus 6.75% grade. The question was what is happening to the speed of trucks on this grade, understanding that because this is a single-lane system ramp, there is no chance to provide a truck climbing lane. Roadway engineering has a truck speed performance model spreadsheet that can be used to simulate what the truck speeds might closely represent on specific vertical profiles. This screen shows the inputs for the spreadsheet. In this case, we wanted to know at what point the truck would drop below 40 miles per hour on a system ramp where the initial speed was 55 miles per hour. The section on the left is the input of the profile grades that represents the entire length of the vertical alignment. This is the output of the table that was created using the spreadsheet tool, considering the vertical profile and the truck weight to horsepower ratio. The highlighted row shows where along the vertical profile the truck is anticipated to drop below 40 miles per hour. This is expected to occur through the plus 4.22% grade and barely into the plus 6.75% grade. By the time the trucks get to the top of the plus 6.75% grade, the speed is expected to be reduced down to 27.8 miles per hour, as shown in the highlighted row. This should be reviewed for LOS impacts based on these slow speeds on this ramp to determine if another profile should be developed. Steep downhill vertical grades can offer challenges as well. They can create increased speeds and out-of-control vehicle performance, as well as an increased risk for rear-end crashes and risky movements. This is especially concerning when combined with horizontal curves. Designers should avoid sharp horizontal curves at the bottom of steep downgrades, but when these must occur, the more warning you are able to provide the drivers, the better. The Ohio Manual on Uniform Traffic Control Devices offers guidance on signs to use. These signs are an example of what is available. Minimum grades offer drainage challenges and can lead to ponding waters and flooding. For uncurbed roadways, there is no true minimum grade if the pavement adequately drains laterally. For curbed roadways, the preferred minimum grade is 0.50%. The absolute minimum grade should be 0.30% and only used when the pavement is adequately crowned and supported on firm subgrade. Drainage calculations would need to be performed to ensure that the spread doesn't extend too far into the traveled lanes. There are some instances where a profile grade less than 0.30% is necessary, though. This is an example along Interstate 270 in northeast Columbus, Ohio. This project was to resurface the proposed main line. However, due to the need to widen the main line, the vertical clearance under McCutcheon Road Bridge, shown on the left side of the profile image, was reduced. As such, it required the proposed profile to be lowered about 5 inches. Lowering this already very flat profile required a section of 0.0% flat grade for about 460 feet in length. To mitigate this flat longitudinal vertical grade, the cross slope was increased to 0.020 to ensure that the cross slope was sufficient to drain the pavement. This section worked because this was in a horizontal tangent where the pavement didn't rotate beyond a normal crown section, and there wasn't any superelevation transition to contend with. If the pavement was rotating and there was a flat cross slope, then you will want to ensure that the flat cross slope doesn't coincide with a flat longitudinal vertical grade. This list represents the reviewer's guide for evaluating vertical grades. Understanding these questions will allow designers to develop vertical profiles that won't introduce significant safety concerns. Section 203.3 discusses vertical grade breaks that can be used without the presence of a vertical curve between grades. Figure 203-2 shows the maximum change in grade without a vertical curve as a function of design speed and driver comfort. Note the minimum distance between consecutive deflections: 100 feet for high-speed facilities and 50 feet for low-speed facilities. One thing to note: when matching into an existing profile or when the graphic grade, say when matching a ramp profile into a freeway interchange gore, check to ensure that the vertical deflections within the graphic grade doesn't exceed the maximum allowable shown in Figure 203-2. The other critical elements of vertical alignments are vertical curves. These are not circular curves, but rather parabolic curves used to provide a smooth transition between vertical grades and are typically centered on the point of intersection of vertical tangents. 3 terms are used to calculate the minimum length of vertical curve. The first is L, the length of the vertical curve. Second is A, the algebraic difference in grades. Final is K, which is the measure of vertical curvature for that specific curve. This coefficient represents the length required for 1% change in grade. There are 2 types of vertical curves, crest and sag. Crest vertical curves are positive grades into negative grades, steep positive grades into less positive grades, or less steep negative grades into steep negative grades. These basically look like the top of a ball. Sag vertical curves are negative grades into positive grades, steep negative grades into less steep negative grades, or less steep positive grades into steep positive grades. These basically look like the bottom of a ball. Let's look at crest vertical curves first. For these, the pavement often gets in the sight line for the driver attempting to see over the curve. For this reason, stopping sight distance for a crest vertical curve is a controlling criteria, and obtaining adequate sight distance is essential to a good design. The image on the right shows the key elements of crest vertical curves. Since the links are based on sight distance, shown in the figure as S, you see how the length of curve L is adequate to allow the car driver eye height, H1, to see object height, H2, without the pavement getting in the way. The two vertical grades intersect at the point of vertical intersection, or PVI. The point of vertical curvature, PVC, and point of vertical tangency, PVT, are located at the ends of the vertical curve. Figure 203-3 shows the design K value necessary to obtain a crest vertical curve length adequate to achieve the stopping sight distance for a given design speed. The length of crest vertical curve should also be designed for driver comfort. Because of this, ODOT looks to establish a minimum length of crest vertical curve to be at least 3 times the design speed in miles per hour, meaning that if the design speed is 50 miles per hour, then the minimum length of crest vertical curve should be at least 150 feet. Let's look at an example of how to calculate the minimum length of a crest vertical curve to achieve stopping sight distance using a 50 mile per hour design and a plus 4.25% grade intersecting a plus 1.30% grade. First, calculate the algebraic difference of the grades. In this case, A equals 2.95%. From figure 203-3, using a design speed of 50 miles per hour yields a minimum K value necessary to achieve the proper stopping sight distance of 84. To solve for the minimum length of vertical curve, multiply K and A. For this example, this results in a minimum length of 247.8 feet. Rounded to the nearest 5-foot interval means the minimum crest vertical curve length for these conditions is 250 feet. Check this against the driver comfort parameter as well, which is 3 times the design speed. With a design speed of 50 miles per hour, driver comfort would demand a vertical curve length of at least 150 feet, which the length we need for stopping sight distance exceeds, so we are good. Now let's look at sag vertical curves. For these, the pavement isn't blocking the sight line. This means that the primary design criteria is headlight sight distance. When a vehicle traverses a sag vertical curve at night, a portion of highway lit ahead is dependent on the position of the headlights and the direction of the light beam. General use is being given to a headlight height of around 23.5 inches and a 1 degree upward divergence of the light beam for the longitudinal axis of the vehicle. For overall highway safety of highways, the sag vertical curve should be long enough so that the light beam distance is nearly the same as the stopping sight distance. Solve the minimum lengths for sag vertical curves like how it was done for crest vertical curves. Figure 203-6 shows how to get the appropriate K value for a given design speed for sag vertical curves. Identify the algebraic difference, A, for the two grades that create the sag curve. When the algebraic difference of the grade is 1.75% or less, the stopping sight distance is not restricted by the curve because the curve is flat enough to not impede the headlight beam using the 1 degree divergence angle. Stopping sight distance is not a controlling criteria for sag curves, but designers should strive to provide the driver comfort as desirable minimum length. AASHTO has an equation that defines the length needed for driver comfort for sag curves, shown here on the right side. The length of curve is equal to A times V square divided by 46.5. A second check is that the sag vertical curve should be at least 3 times the design speed in miles per hour, like what is done for crest curves. Make sure to coordinate the sag vertical curve design with the super elevation transition design to ensure the low spot of the vertical curve does not align with the flat spot of the super elevation transition. Also, avoid excessively long sag vertical curves. Providing too long of a vertical curve can be problematic for drainage if within a curb section. A K value of greater than 167 should be avoided because it traps water at the bottom of the vertical curve and can create standing water. If you find you must provide a K value greater than 167, then investigate steeper lateral pavement cross slopes to get the water channeled to the outside of the roadway as quickly as possible. Let's look at an example of how to calculate the minimum length of a sag vertical curve using a 45 mile per hour design and a minus 3.25% grade intersecting a minus 1.90% grade. First, calculate the algebraic difference of the grades. In this case, A equals 1.35%. This means that the pavement through the curve does not impede sight distance. From Figure 203-6, using a design speed of 45 miles per hour yields a minimum K value necessary to achieve the proper stopping sight distance of 79. To solve for the minimum length of vertical curve, multiply K and A. For this example, this results in a minimum length of 106.7 feet. Check this against the driver comfort parameter of 3 times the design speed. With a design speed of 45 miles per hour, driver comfort would demand a vertical curve length of at least 135 feet, which exceeds the length we need for stopping sight distance. Checking also AASHTO's driver comfort equation results in a length of 58.79 feet. Given these 3 values, the minimum curve length should be 135 feet, as that value exceeds the length required for stopping sight distance, AASHTO's driver comfort length, and meets at least 3 times the design speed. It is important to avoid the roller coaster profile that can often hide obstructions between vertical curves. Designers should provide as smooth of a profile as possible using gradual changes in vertical grade. Similar to horizontal alignments, short tangents between the same types of vertical curves should be avoided. In the event these occur, or in a situation where the vertical curves are short and closely spaced, a graphical calculation of the provided sight distance may be necessary. If sight distance is not provided, look to provide warning signs to alert drivers of potential hidden objects that could be present, such as the sign shown in the image on the right side. We can't discuss vertical design without discussing vertical clearance. This is discussed in Section 302 of the L&D Manual. These are the vertical clearances for various roadway types provided by AASHTO and the L&D. Note that the vertical clearance must be provided over the lanes and the shoulders. This table is for new and reconstructed bridges, which are bridges that at a minimum are getting a deck replacement. Vertical clearance is a controlling criteria, so a design exception would be required if the required vertical clearance from this table is not provided, even if following the reduced vertical clearance value referenced in Note A. If a design exception for vertical clearance is required, the designer should be prepared to check sight distance, recent crash data and trends, and availability of alternate routes that can provide the required clearance. Let's also look at sight lines to overhead guide signs that could be blocked by overhead bridges. Shown in the bottom right is Figure 298-11 of the Traffic Engineering Manual. Designers must position overhead signs such that they are visible within adequate approach distance for drivers to be able to see, read, comprehend, and make a decision without an overhead bridge being in the way. Not providing adequate distance for drivers to see overhead signs could lead to erratic driver behavior because of abrupt lane changes and can lead to a safety concern. This table is for bridges to remain with less work being performed to them than a deck replacement. This could mean a parapet replacement, patching, joint repairs, or other minimal maintenance efforts. This module walked through the critical elements of vertical alignments and discussed the types of vertical curves used in highway design. These key terms were discussed in detail in this module. A detailed explanation of how to design the proper vertical alignment to obtain adequate safety performance was included in this module, as well as a brief discussion of the appropriate mitigation to use when the design doesn't meet standards. This module should have provided you with the philosophy needed to create and check well-designed vertical alignments.